the column space of A, so it's the collection of such a vectors Ax where x are from An actually. So you can treat this as really the range of the A. It's not really the range of A, but the column space of A actually. Okay. So in other words, it's the collection of the A multiplied with every single vector in Fn. So if this is a vector in the column space of A, then this is going to be Ax naught. So A multiplied by what do you call some x naught actually. Okay, and the vector that is orthogonal to it is going to be what? So if this is y and this is Ax naught, then this is really y minus Ax naught. Okay, so this is really y minus Ax naught. So what we're gonna do? We're gonna take this y, orthogonally project. In other words, we're gonna compute the orthogonal projection of y onto the column space of A, which turns out to be Ax naught. And you can always find such orthogonal projection. And what do you call that? Would be the Ax naught. B would be the really solution of what do you call our x naught is going to be the solution of this system, which minimizes. Okay, which minimizes the square of distance between Ax naught and y, because this is 2 naught. Okay, so let's prove it quickly. So here's the proof of the result. So consider a matrix A that has columns A1, A2, An. So these are the n columns of the matrix A. Okay? And U is the column space of A, which is the span of these column vectors A1 up to An actually. Okay? Now what we have been said, or what we can do actually, we need to find the orthogonal projection of y onto what do you call the column space of A. So in order to, we need to find what you call the orthogonal projection of y onto the column space of A. So if you want to find, and that will be the best approximation. So what is the orthogonal projection of y onto the column space of A? So it's going to be a vector. Okay, is going to be the sum of the vectors that goes like this: I equal to 1 to n, Ci and Ai. Okay, so this is what that you're going to get. Now what are Ci's actually? Ci's are the solution to the normal equations. Okay, they are solutions to the normal equation, you know, AC equal to B. Where what is matrix A? The matrix A is like U1, U1, okay, U2, U1, and so on and so forth, and UN, U1. Or if I write it directly, so what is the norm on, say, Fn actually? Okay, so the norm on Fn is that if you have two vectors x and y in Fn, so it's y star x actually. So this is what the norm in Fn. So the matrix A, let's not call this A, let's call it something else actually. Okay. Let's call this, for example, matrix B actually. Okay. Or matrix, I don't know. Let's call this matrix M. Okay. Where the M is really the inner product of these vectors, An vectors actually, which were U1, U2, Un in previous case. So it's going to be A1 is star, what do you call A1, and A1 is star A2, so on and so forth, and A1 is star An. And the last row is going to be A2, no, An is star A1 up to An is star AM. So this is going to be the last row. I mean, if you see this carefully, this is nothing. This is just the matrix A multiplied by the matrix A star actually. Okay, so the A star matrix multiplied by the matrix A. Okay, so this is what is this matrix M. Now what is C? C is obviously the matrix that consists of C1, C2 vectors Cn. And what is B? So B is the inner product of, in theorem it was V with the UI's vector. So now here we have Y actually. So this is going to be A1 star Y up to AN star Y. Okay, AN star Y. So what you can do? So I mean, what is this quantity? So this quantity, if you see carefully, is nothing. It's A star Y actually. So this is A star Y. Hence, by the way, this system in the previous theorem is always consistent. So therefore, this M matrix is going to be, what do you call, A star A times C equal to, what do you call, A star Y. And since from the theorem about the normal equation, this system is consistent, so this is consistent actually. So if this is consistent, so there must exist an x naught from Fn such that it satisfies A star A x naught equal to A star Y actually. Okay? So there is always a solution to this. So if you have, what do you call, an orthogonal projection, okay? So if you want to orthogonally project the vector Y onto, say, the column space of U, then this is the best approximation of the Y in the column space U actually. So it's the best approximation, okay? So what we would like to do, we would like to find the best approximation of Y in the column space of A. Now, in order to find the best approximation of Y in the column space of A, we computed the orthogonal projection, because the orthogonal projection of Y onto the column space of A. Why? Because orthogonal projection, okay, of a vector onto a subspace is the best approximation actually. So if you want to find the best approximation of the vector Y in this space, you need to find the orthogonal projection of the Y onto the column space of it. So we found that orthogonal projection, okay, you know, by computing these C's, which can be computed by solving this system, in which the M matrix, which was the matrix of inner product, is like that, and the matrix B is really what you call A star Y. And this system is consistent. So in other words, if I substitute the value of A and B, this system is consistent, and hence there is a solution to it actually. So if there is a solution to it, this system is consistent, and if this system is consistent, you can find C, and if you can find C, you can find what you call the orthogonal projection of Y in the column space of A, which is the best approximation of the Y in the column space of A. So this really proves the if and only, what do you call, if statement actually, okay? And we also know that if the rank of, so the theorem about the normal equation. So we know that if the rank of A is n, in other words, these column vectors are in the matrix A are linearly independent, then the system, this system has a unique solution. So if this has a unique solution, that means this has a unique solution. Okay? This has a unique solution actually. So if this has a unique solution, that means that there is a single x naught, okay, which best approximates there is a single x naught for which the ax naught best approximates the y, okay, in the sense of the two norm actually. So I hope this is making a little bit of what do you call, sense to you, okay. put some remarks and then come to the little bit of application of this, do this a bit more explicitly. So, here's a little remark. If the null space of A is non-trivial, okay? The null space of A is non-trivial, then there can be many x naught. There can be many x naught. In other words, this system A star A x naught can have many solutions actually. Okay, can have many x naught. Okay, that satisfy this system, this solution, but that satisfy a star system, a star actually. But for all of these x naught, there can be many actually, but this orthogonal projection, so PU of y onto what do you call the column space of A, which is what do you call AX naught, this number is going to be same actually. This is going to be same for all x naught that satisfies star. So this is the first what do you call remark actually. Now if the rank of, you know that in advance that the rank of the matrix A is n actually. Okay, so all of these n vectors are linearly independent. Then we know that there is a unique solution. But the question is, what is that unique solution? So we know from our previous knowledge that if the matrix of array n is a matrix of rank of A is n, then the matrix A star A is invertible actually. Okay? So you can always find the inverse of it. And if this is invertible, then I can throw this A star A onto the other side. In other words, so I can find a unique x naught, which is going to be, so if A star AX naught is A star Y, then x naught explicitly is going to be A star A inverse times what do you call A star Y actually. So this is what is going to be the explicitly A star A inverse x naught. And if you have an explicit expression for what do you call x naught, then question is what would be the orthogonal projection. So we know that the orthogonal projection of y onto u is this Ax naught. And if x naught is this, that means that the orthogonal projection is matrix A multiplied by A star A inverse and A star Y actually. Okay, so this is really going to be the orthogonal projection. And if this is the case, then you have another interesting result as well, that there is explicitly a matrix for this orthogonal projection. So the PU, the orthogonal projection of U, which is really the column space of A, okay, the matrix representation of this linear transformation is basically this matrix A star A inverse A, the star. Okay, so this is what is going to be the matrix representation of the column space of A actually, or the matrix representation of orthogonal projection onto the column space. So either you have many x naught, okay, that satisfy star. All of these x naught are going to give you be the best approximation of y in the column space of A. And if the rank of A is n, then this x naught is unique, which is this number. Okay, you can directly compute this, and you can also compute the orthogonal projection explicitly in such a case if the rank of the matrix A is n. In other words, that all n column vectors are linearly independent actually. Now let's think about one application of this theorem, which is like best fitting. So if you have been given a set of points, so imagine, as I said, you have this xy plane, okay, in which you have, for example, several points. Okay, I don't know, that goes like this actually. Okay, now the question is, so the question is, can you find, for example, two equations, okay, that pass through all of these points? The answer is no. You can't find basically, such an equation that are such a set of equations that pass through all these points. The question is, can you find one equation that kind of best fits this data, for which the distance between all these points and that line is minimum actually? I can draw several lines. So this is one line, okay, and say this is another line. But if I compute the distance between these points and the line, these points and the line, these points and the line, for example, these distances are bigger as compared to this line actually, as compared to this line. Okay, so if I, for example, assume this line, so I'm going to say that, okay, all the points, these discrete set of points, has a minimum distance between the line and the points as compared to all other lines actually. So I'm going to say this is the line, okay, which we, social scientists said this is the regression line that best fits the data actually, that best fits the data. Okay. As an application of this result, we will basically formulate a methodology for finding this best fit actually, okay, for which the distance between these points and the line is minimum. Okay, so if we have been given these points in the plane, can I find such a line which best fits all these points linearly? What do you mean by the best fits all these points linearly? The distance between the points and the line is minimum as compared to all other lines actually that you draw in the plane. Okay. So imagine I have been given a set of points. I have been given the thing that I'm doing. This is also called the method of least squares actually. It's a very popular method in statistics and what you call in social sciences. People use it a lot. But at the foundation of this method, this theorem and hence orthogonal projections are working actually. Okay. So what does the method of least square say? So it says that imagine you have set of points x1, y1, x2, y2, so on and so forth, xn, yn. Okay, so these are the points, what do you call, in the plane. So what we will like to do, so what is our goal? Our goal is to find an equation y equal to ax plus b, okay, what do you call y equal to ax plus b, a line that best approximates the linear relation actually, okay, that best approximates all this data linearly. Okay, linearly. So this is what that we would like to, what do you call, find actually. Okay. So if all of these points, so I know that all these points are not necessarily on this given line. So this is a given line that I'm interested in. I want to find A and B. But all these points not necessarily lie on, what do you call, you know, this line actually. Okay. So if they don't lie on a line, they lie on some other lines. So say that this x1, y1 lies on a line whose equation is, say, y1 equal to ax1 plus b, and y2 is ax2 plus b, okay, and so on and so forth, and similarly yn is axn plus what we call b actually. Okay, so you can write all of these equations as a system y equal to ax. So this system y equal to ax is an inconsistent system actually. Okay, this is an inconsistent system, so you can't find, you know, an x for which you're gonna get, so you can't find a vector x whose components are x1, x2, xn, okay, such that that gives you what you call the y, okay, because all of these points do not lie on the same line actually, so you can't find what you call a solution to this system where, let me write it y explicitly, the y is really y1, y2, yn, the matrix A is say x1, 1, x2, 1, and so on and so forth, xn, 1, and the vector x, okay, vector x which is unknown to me, a and b is this, and y is this. So if you take, the question is that, you know, obviously you can't find the solution of this system because there are, you know, more equation and less unknowns actually, so the system is inconsistent. Okay. What would be the rank of the matrix A? So if the rank of the matrix is say 2, okay, you can also say that since all these points do not lie on a line actually, so therefore, you know, the columns of the matrix A are linearly independent. So if they are linearly independent, they are not multiple of each other. Because if they are, they will lie on the same line. So they are linearly independent. So if they are linearly independent, the rank of the matrix A is what do you call unknown. Okay? So you have n equations for which you need to find what do you call two variables A and B, and you want to find. So this system is obviously inconsistent. So if this system is inconsistent, then this previous theorem ensures that there is an x naught. Okay? So if this system is inconsistent, this system y equal to ax is inconsistent, then this is star is inconsistent. Okay, so it's inconsistent. Then this previous result guarantees that by solving the system A star A x naught equal to say A star y, okay, or maybe A star A x equal to y, this system is always consistent. So if you solve this system y, you can find an x naught, okay, for which the distance between y and x naught in 2 norm is minimum actually, okay, is smallest, is minimum. This is minimum. But what is this distance explicitly in 2 dots? So y is the vector y1, y2, yn, and ax is the matrix, ax1, ax2, what do you call, ax plus b actually. So what would be this distance if you want to write this explicitly? Okay, so it's going to be the square root of, so this is the square root of the sum I equal to 1 to n of yi minus axi plus b square. axi plus b square. Okay, square. So this is really the case that you solve this system. Okay, you're gonna find an x naught for which the distance between y and ax naught, this number is the minimum actually. So you're gonna say that x naught is the closest or the best approximation, okay, of what do you call this given data actually, or this system of equation, okay, or the solution of the system of equation actually. And from this you can find an equation that best fits the data. So let me do one example that kind of shows this more explicitly. That if you have been given a set of data, so imagine if you have this system 0, 1, say 1, 1, 2, 3, 3, 3, and 4, 4. So these are, for example, the points. And I want to best fit a line y equal to ax plus b. I want to find a and b for which the distance between this line and distance between all these points and this line is minimum actually. So this is what that I would like to, find. So how can I find it? I need to solve a system y equal to ax, okay, where y's are what values? So y's are really these values. What values? 1, 1, 3, 3, 4. Okay, so y's are these values. 1, so 1, 1, 3, 3, 4. This is y. Okay, and my x is AB. Okay, and my matrix A is these coefficients, first coefficient, first component with 1, 1, 1. So 0, 1, 1, 1, 2, 1, 3, 1, and 4, 1. Okay, so this is what is going to be. And if you want to solve this system, obviously this system is inconsistent, but if you want to find a best approximate to the solution of this system, you need to solve this system actually, which is A star A, okay, A star A x equal to A star y. Okay, so obviously A star is A transpose because these entries are real. So what you can basically see that when you're gonna multiply A star with A, this is going to be 30, 10. Okay, so 30, 10, 10, 5 is going to be 2 by 2 matrix because A is 1, 2, 3, 4, 5, 5 by 2, and if you transpose it, it's going to be 2 by 5. So 2 by 5 matrix multiplied by 5 by 2 is going to give you 2 by 2 matrix. And AB, this is x, and my A star y is going to be 32 and 12 actually. Okay, so A star is